Okay, welcome to another lovely day in geology land. And I'm going to start off with, I just have a quick list of all the things that we have going on right now. I told you yesterday I'd get the next homeworks up, and so they are currently up. I will continue to try to grade your homeworks and your labs. In fact, right now, so grade the labs at home. Yeah. The lab key in my backpack so I can go home and grade the labs. So you all should be working on the river lab. I gave that all to you in online, people. You should have the instructions for the river lab and the file for the river lab. And I will double check everything's good on Canvas. Know that that's due Friday, so 2 days from now. Make sure you have that done and submitted. And the in-class students can submit it in person. Online students scan it or take a picture of it or email it to me, or maybe just bring it by the front office and have them stick it in my box if you don't want to do that. So chapter 3 and 4 homeworks are now up on Canvas. So we've already lectured on chapter 3. We're probably halfway through chapter 4. I'm going to give you some time on that to make sure everybody has time to work through it. So those are going to be due Friday the 16th, and I believe the due dates in Canvas will reflect that. And as usual, when the homeworks are due, that's when we're going to have our test over those chapters. So the next test in this class will be Friday the 16th for chapters 3 and 4. We will finish up chapter 4 today. And so we're actually going to start lecturing on chapter 5 sometime this week. There's a lot of stuff to go over in chapter 5, and we have another lab for chapter 5. So I just want to get an early jump on it so we have plenty of time to do it. And I think chapter 6 as well, there's probably another lab. Hold on. Come on. We'll let that warm up. Let me see what chapter 6 is. Chapter 5 is plate tectonics. Chapter 6 is earthquakes, faults, and mountains. So yes, we have labs for both of those chapters before we move on to something else. Wonderful, wonderful. So yesterday, we kind of left off somewhere around here. And for the online students, I'm going to try to make up a video for y'all for yesterday because it didn't record properly. We left off talking about glacial drift. Glacial drift is any sediment that of a glacial origin that the glacier mechanically wears down and then erodes downhill as it moves. There's lots of different types of glacial drift. One of them is till. Till is a material deposited directly by ice when it melts. So it's just stuff that the glacier kind of picks up as it's moving. And then when it melts away, it just literally drops it right there. When we get to the next page, which let me get my pen. When we get to the next page, they're going to talk a lot about moraines. All the moraines are made out of till. So till is what builds up your moraines, and moraines are more like the physical structure that's made up of the substance till. They talk about stratified drift, which is sorted and deposited by glacial meltwater. So just like we talked about in the river section, how you have different periods of rivers that move faster and slower. So it picks up big stuff, drops it, drops the medium stuff on top of it, and then light stuff, and you get this kind of sorting by size. That's what's going to happen in your stratified drift. And then your glacial erratics. I know I got to that in this class. What? Nothing's working this morning. So we talked about erratics basically being like the giant boulders that get picked up by glaciers and then deposited in an area that they don't really look like they should be there. So boulders different from the bedrock found in the till or underlying surface. So yes, here's some erratics, and you can see these giant boulders. out in the middle of a field that doesn't really look like it should hold boulders like this. There might be some mountains nearby, but it's not. These aren't boulders that look like they rolled down the mountain and rolled out into the middle of the field, and so they're kind of out of place here. And I do think yesterday we got to this picture that shows this giant pile of till. This would be a moraine. Without the context of where it's at or where the glacier's at, I don't know what type of moraine it is. But this giant pile of till is a moraine. And then you can see the larger pieces inside look really roughed up. Like they've been dragged across the ground. They've been smashed into other rocks. There's gouges and scrapes and stuff on them. And so that's really what a glacier does is it pushes, it smashes, it grinds, and you get a lot of effects of that nature. So when you're talking about till, and they mention it here, moraines are layers or ridges of till. There's 4 different types of moraines that we look for. Your lateral moraines form along the sides of the valley. So as your glacier moves downward, some of the grinding that happens on the sides ends up making these lateral moraines. The end moraine is literally at the end of the glacier, and when it starts to melt back, it will just drop all the rocks there at the very end, and you get your end moraines. Medial moraines, let me actually go back a couple slides. Medial moraines will be like these right here. And so you have these these lateral moraines on the side, and then when the 2 glaciers meet, these moraines get dragged out into the middle. And so as this glacier would melt back, you would have these 2 pretty large ridges of just grinded up rock and material made up from the weathered stuff from the glacier. And so these are going to be your medial moraines all the way up until the point the glacier split, and then they'll become lateral moraines. So that's what they mean by medial. Oh, way far back. Come on. All right. And then ground moraines are gently rolling layers of till deposited as the terminus retreats. And so we're going to see a couple of these in the very next slide. This is a map just showing you some of the moraines that we have in the United States. The red ones are from the Wisconsin age, and then the purple ones are from the Illinoisan age, which is a weird word. Note they're all kind of around the Great Lakes, which were formed by glacial activity. And you can see the kind of layers as the glaciers advanced and then retreated back. And so you can kind of almost see from the moraines the direction and the extent of the glaciers, and then as they retreated, what they kind of looked like doing that. Pretty interesting. If I'm going to get to this, let's look at the moraines first before we get into more terminology. So here is an end moraine. You can see that the glacier came all the way out to this point. This was its furthest extent. As it started to melt back, it left that leading edge of till and just kind of dropped it there in a giant pile, which became the end moraine. As it retreats more and more and more, these are going to be your the ground moraines. So they don't have it labeled here, but this would be a ground moraine. And then they have a couple other features which we haven't fully gotten to yet. Note that this picture doesn't show lateral moraines or medial moraines because it's just kind of like a slice of the glacier. Let's go back and look at a couple more terms from this. Braided meltwater streams. So we've already talked about braided streams in the rivers chapter, the chapter 3 just before this. It literally looks like it's braided out. And usually the reason for that is you have low water flow, so not a whole lot of water, but high sedimentation. So the sediment kind of clogs up the river and doesn't allow it to flow in one solid channel. It kind of forces it to break up and come back together. And so that kind of makes sense with a glacier. It's going to melt a little bit, so you're going to have some water, but it's not going to be producing an immense amount of water, but it should be producing a lot of sediment as it grinds everything up as it goes downhill. So braided meltwater streams are pretty common coming out of the end of a glacier. They have the outwash plain, which is associated with ice sheets. So that's a much larger glacier. So you should have a lot more water kind of coming out from that. And then a valley train is confined to a mountain valley, and we'll see. I think we'll see that. Um, Four more here. Kettles are basins or depressions in the outwash plain formed by buried ice that eventually melts. They're about 2 kilometers and less than 2 kilometers in diameter and less than 10 meters deep. They're kind of like little pools in a way, nice and round. Drumlins are streamlined asymmetrical hills made of till, and you'll see those in the next one. They're almost like till that's been kind of stretched out as the glacier retreats. They look pretty weird. If you saw one out in the middle of a field, you wouldn't look like something that's kind of natural. But glaciers do weird stuff. Eskers is sinuous ridges of sand and gravel made by the streams flowing in tunnels underneath the ice. And then cames are steep-sided hills of stratified drift. Here we go. So here are your drumlins. You can see that they're like stretched out. Like you can see this. This is like farm fields here. If you saw this, you're just walking out in the fields out here in Palmer, Texas, which it wouldn't be out here because we have no glaciers. But this would look really weird. You'd be like, what? Like, why is this here? And your first thought before you inspected it might be, oh, well, this could be like a different type of rock that just didn't weather the same way as all the surrounding material. But then you go in and you inspect it, and it's not a different type of rock. It's just like a pile of rocks and dirt and sand. And so it really doesn't seem like something that would naturally just be dropped there. But that's the way the glacier works. As it retreats, it kind of leaves these scraped out hills of material. So that's a drumlin. Here are your kettle lakes. And so you can see they got a couple of these here. These might be even kettle lakes too. Just a deep depression made by the ice that's not really level with anything else. Not super huge, but pretty big. So that's a little kettle lake. Here's your braided river coming out from the glacier. So you can see it moving out here. They have some eskers, which are caused by like basically river flow underneath the ice as it tries to retreat, because this one's retreating out. It's not coming all from the melt at the front. It's actually coming from the melt at the bottom of the glacier and coming out from underneath it. So as it travels underneath the glacier, it's going to push sediments up into this nice ridge and create the esker. And then they have some cames. These are like little round hills, almost like shortened versions of drumlins. So not as asymmetrical, not as stretched out, but these big kind of lumpy hills. So these are all weird things that we don't have around here and we're not familiar with because we live in the Texas hellscape that is summer, and there's never going to be any glaciers anywhere around here, unless things go terribly wrong. If you wake up one day and there's like a glacier approaching your house, you know that we've done something very, very bad. So what type of sediments are deposited and generated by glaciers? Till is going to be a blanket term for almost every kind of sediment that gets deposited by the glaciers. You have stratified drift, which comes out in the meltwater, so the streams. And then you have these giant glacial erratics, which are transported by the ice and literally just dropped in the middle of nowhere. So those are kind of the three big parts of that. Okay, so we're going to talk a little bit about effects of glaciers. This won't be too long, and then we're going to get into deserts, like the polar opposite. So what are some effects of ice age glaciers? Forced migration of animals, alterations in stream courses, rebounding of land, and just to hammer home the forced migration of animals and maybe the rebounding of land. Oh, that was a different one. Let me go back forward then. I don't have it pulled up. But remember the picture I showed y'all yesterday of the glacial extent in the last ice age where all of Canada was essentially covered with ice? Unless you're an ice-dwelling animal, you'd have to migrate. Like there's no way that you live up there in any meaningful way. All the grazers, most of the birds would have to migrate south because they just can't live on an ice field like that. And that would probably go for people as well. I doubt there was very many Canadians residing just on the glaciers themselves. So there's not going to be any animals eating there because there's no grazers. It's just going to totally change the biologic diversity. Rebounding of land. Think about how heavy like a bucket of water is. If you have literally a glacier covering your entire continent, that's going to push down on the land. It's going to push it down, even if it's just a little bit. That is a lot of extra weight. And then when all of it melts, which usually happens pretty quickly, all of it melts and goes away. That land is used to being pushed down. It's going to kind of rebound. It's going to push up a little bit, which can cause faults. It can cause all sorts of other geologic things to happen. Ice sheets dam meltwater and create lakes. They call these proglacial lakes. I don't know why I had so much trouble with that. Worldwide change in sea level because you have a lot of water that would normally flow in rivers all the way out to the sea, but it doesn't do that. And so when you have glacial highs, you have lower sea levels. When you have glacial lows and there are almost no glaciers, you have higher sea levels. So up to 100 meters lower during the ice age. And when the ocean's lower, you in some places have more land. So it's just not where you want it to be, I guess, because some of your land, like Canada, is just completely covered up in glaciers. And then you have pluvial lakes formed during the cooler, wetter climates. So what they're showing us here is changing of rivers before and after the ice age. So this map shows the Great Lakes and the familiar present day pattern of rivers. Quaternary ice sheets played a major role in creating this pattern. So the Great Lakes here, and then you have the Mississippi, which comes all the way from Minnesota and comes all the way down the country, joined by a lot of other rivers, including the Illinois River, the Ohio River, the Missouri River. That shouldn't be allowed. That's not the Red River. That's cheating. We have the Red River. That's it. And then they show down here reconstruction of drainage systems prior to that ice age. So by doing digging and different scientific geological work, we can see where the riverbeds used to be. And you can see that the Mississippi branched out quite a bit more. Let's look at some of the differences here. The Missouri River changed quite a bit. So you have the lower Missouri coming out over here, where in the present day it comes more north for quite a while and ends up coming almost up to the Canadian border, where it did not really do that previously. It had a very different path. The Ohio River was not nearly as long before. Now it comes all the way up into the New England area in a way. And you had this Tejas River, maybe? I don't know how you pronounce that. Tejas. It comes all the way over here, and it's not really in existence after the ice age and the glacial maximum. So, and then you have a couple other river systems that end up being covered up by the Great Lakes. They kind of have the shadow of the Great Lakes here. So the glaciers help to really carve that out and make those permanent bodies of water. What is this? Other effects of the ice age. So these are probably going to be just after the glacial maximum. So the glaciers come down, cover a large area of this. This is the Canadian border here. You'll know this because you see foreign words like Saskatchewan. So this is mostly Canada. You have the edge of your Great Lakes over here. So the Great Lakes would be further over here off this image. But as the glacier retreats, not all that water is immediately going to make it into the rivers and streams and go into the ocean. And you've had a giant glacier literally pushing down on this for probably thousands and thousands of years. And so the land is a little bit depressed. And so when it melts and the glaciers retreat, a lot of that water ends up staying right here. And so this would have been a giant, giant lake covering a huge portion of Canada. There's an outlet that goes into Lake Superior, and I believe all the Great Lakes they're all salty, right? And connected to the ocean. Maybe? No? Yeah, I might be wrong about that. I should probably know that, but some of them are connected to the ocean, I believe, at least by rivers. And so that could be the way that a lot of this drained out, is by draining into the Great Lakes and then the Great Lakes slowly draining into the ocean. So yeah, there you go. During the last glacial maximum, which was about 18,000 years ago, sea level was nearly 100 meters lower, and they kind of show that. So here's the sea level curve. Here is the present day level. Here is about 18,000 years ago, the last glacial maximum. And what they're showing you here is extended land because of that sea level drop. And so Texas actually has quite a bit more land, if Texas was a thing back then. Florida's huge. The panhandle for Florida is huge. And you could almost walk from Cuba up to Florida here. Actually, I don't know that that's Cuba. Is Cuba further up? I don't know if that giant long one's Cuba. I'm bad with my geography. But yeah, nice big coastline out here for the Pacific, or not Pacific, the Atlantic Northeast. Yeah, there's probably a lot more land coming way out here too. Interesting. So I like old maps like this. And then here are some more. This is out in California. The Great Salt Lake is a remnant of Lake Bonneville. Lake Bonneville is nearly the size of present day Lake Michigan. Did they have glaciers out here though, or is this more just like glacial melt that was happening? I'll have to look that up in the book. Let me look and see. Okay, so we're almost to the end of the glacier part. They're not leaving very much time for deserts. So the last ice age began between 2 and 3 million years ago. So know that the last glacial maximum, while we had a lot of glaciers there, was not an ice age. It was just a cold period where we had glacial advance. An ice age is much, much more complete and serious. So the last ice age began between 2 and 3 million years ago during the Quaternary period. Ice sheets and alpine glaciers were far more extensive than they are today. Almost 30% of Earth's land was glacially influenced. And so you can see that the glaciers here are really coming down further than that last glacial maximum. Most of Canada is gone again. Greenland's completely covered. And you have a lot of glaciers even going down into Russia. And it looks like most of Europe is covered up as well over here. They have the Alps right here. So definitely the northern part of Europe is covered up with glaciers. Okay, so then they segue to deserts pretty abruptly there. I will say there's a question on the homework that asks about geologic periods and ice age, and there is a geologic period that the name of it is basically a shorthand for geologists to say ice age. It's not the Quaternary period. It's a different name. So if you have trouble finding that, let me know, and I will try to send you a link to help you figure that one out. But I looked it up last night, and it wasn't too hard for me to find, but I didn't even remember it off the top of my head. So get some water. We'll get into deserts. Okay, trick question. Not really a trick question, just something you may not get right. What's the world's largest desert? Yeah, you gotta think about it because I already told you it's a trick question.
Oh, Antarctica.
Yes. It's Antarctica because Antarctica, although it's cold and we think of deserts as being hot, the definition of a desert is all about rainfall and precipitation. And while Antarctica does have ice on it, it doesn't get a lot of precipitation. So I don't know if they'll mention that here, but remember when we talk about deserts, the definition of a desert has to do with its dry climate. It's not always the temperature. Now, most of the time, it's associated with hotter temperatures and hotter weather, but that's not always the case. So 30% of Earth's land surface is arid. Doesn't get a lot of rain, doesn't get a lot of precipitation. It's mostly concentrated in the subtropicals and the middle latitudes, affected by many geologic processes like mountain building, running water, wind. So in order to get a desert, you need to have a dry climate. Your yearly precipitation needs to be less than the potential loss of water by evaporation. So if you're going to call it a desert, it needs to be arid. We have a subcategory, which is called a steppe, which is semi-arid. So it's going to get a little bit more moisture, but it's still going to be considered a very dry climate. So here are your deserts by map. You have your actual arid deserts in yellow, and your steppes, which are semi-arid, in the more like pea green or like brown green. It's not this green; it's that one in between. So obviously the Sahara is very large. If you're not including Antarctica, the Sahara Desert is going to be the absolute largest. It covers a huge portion of Africa. This might be a pretty good map. This doesn't show the actual ratio. Know that map making on flat surfaces is really hard to get it right. Either the shape's going to be wrong or the size is going to be wrong. And a lot of maps, the United States and its size, not just the United States, all of North America and its size is greatly exaggerated. This one's probably right because you can really see how much bigger Africa is than North America, which is absolutely true. Africa is very large. And so the Sahara Desert, if you look at it size-wise in this map, which I don't know if that's area-wise accurate, it's almost as big as the entire United States. So the Sahara Desert's pretty large. The Arabian Peninsula is a very large desert, which is interesting. When you study oil and gas, you learn that while the Arabian Peninsula has a huge amount of oil and gas, oil and gas does not form in desert environments. And so the vast majority of the Arabian Peninsula's history has been spent in more tropical climates, not in desert arid climates, which is kind of interesting. You got a couple. This wouldn't be Eastern European. This would be more Western Asian deserts over here in the Turkestan area. I'm trying to think of the other names of this country. A lot of them end with Stan, like Kazakhstan and Pakistan's more in the Arabian Peninsula. But in these like former republics of the Soviet Union, that's a good way to describe them. Although they probably wouldn't like that. And then Australia. Know that the vast majority of Australia is like a desert wasteland. Most of the people in Australia live around the coast on the very edge. And then driving from one coast to the other is just like a multi-day nightmare of nothing. And giant spiders. Don't live in Australia. You can visit because I'm sure it's a nice vacation, but I wouldn't want to live there, especially in the middle part. So yeah, these are your deserts here. We also have a couple deserts in the western United States. So they have the Sonoran Desert, the Mojave, and then down in Mexico, which actually stretches a little bit into Texas, you get the, would that be Chihuahuan? I don't know. I'm not even going to try to pronounce it. I won't do it well. But it's like the dog breed. So my pin crap out right in the middle of a power. I'm on a desert slide. Pin stopped working. It's unacceptable. I need to submit a work order for this, and maybe I'll get a new board. Wouldn't that be wonderful? I'm gonna have to do that today. I've been wanting a new board for years. Come on, we need to get through deserts. We don't want to drag this into another day. How much time do we have left? 12 minutes. We can do this. Okay. So African, Arabian, Australian deserts are a result of prevailing winds. So basically the wind patterns that they have globally just don't bring them a lot of moisture in. It depends on which direction your wind's coming from. how warm the water is if it's coming over some water. So subtropical highs in the lower latitudes. We'll talk about weather later. It's probably one of the last chapters we kind of do. Subsiding air is compressed and warmed, and you just don't get very much moisture that comes out of that, creating clear skies and ongoing dryness forever and ever and ever. Your middle latitudes, deserts, and steppes occur in the deep interiors of large land masses. So if we kind of go back here, like Australia has lots of area that isn't desert, but just once you get inside that continental area, not a lot of moisture carries over. And if you look in the United States, with these kind of being the exclusion here, we have several deserts on the eastern side of mountains, because in order for this air that's nice and moist from the Pacific to get over those mountains, it has to go up where it loses its capacity to hold water. It drops all the water in the rainy states like Washington and Oregon, and by the time it gets over the mountains into the other side like Wyoming, Idaho, Montana, you lose a lot of that moisture and it just doesn't drop very much. Some other interior deserts that they're talking about would be like in this area. You've got large areas of land surrounding it, and to the west you do have some little seas, but not enough to really provide you a lot of moisture. They get little precipitation because of their distance to the ocean, and because of mountain building. So they're going to show you a little bit of weather. We're not going to get too deep into that, but know that in general, for the vast majority of the year, your weather patterns kind of follow this area. And so they're pulling this area away, which is why a lot of Mexico is very dry, because you're not getting the winds coming from the ocean in either direction, bringing you a lot of moisture. Your winds in Mexico are kind of coming down from the continental landmass of the United States, which is also why we don't get rain a whole bunch here in Texas. We're not like arid or semi-arid or anything, but in general, a lot of our wind and air masses comes from the middle of the country, and so it just doesn't contain as much moisture as we would probably like most of the time. I'm a rain person. I like rain. Some people are all like, "Yeah, it's raining. It's sad." Give me rain most of the time. So here's the mountain effect, the rain shadow caused by mountains. As your moist air comes in from the oceans, it has to be pushed up. When it's pushed up, it loses its pressure, and it loses its ability to hold water. So the dew point changes. It literally drops all its water on one side of the mountain ranges, and then on the other side, as it comes back down, it just doesn't have any water in it. And what little moisture it does is not at the right pressure and conditions to actually cause precipitation. So on one side of the mountain range, you'll have nice lush forests. On the other side, you will have kind of scrubby land with not a lot of trees and not a lot of rain going on it. All right, so now we're going to talk about some water features in deserts. Ephemeral streams. Someone look up ephemeral real quick, just so we get. I'm thinking, when I think of ephemeral, I think almost like ghost-like, but maybe I'm thinking of something different. But ephemeral streams can only carry water during specific rainfall events. So these are going to be desert streams that literally, like 95+% of the time, are just completely empty. And then when you get the rain, the flash floods, the like monsoon season, they fill up and become nice streams.
So ephemeral means lasting for a short time. So it's just like short.
Okay, lasting for a short time. I don't know why it's making me think of ghosts, but it doesn't really relate to this. But something in my head was like, that's like ghost-like. So you have little vegetation to mediate runoff, like in deserts. There are cactus and different scrub brushes and stuff like that. They're not going to be able to soak up enough water to keep it from running off into the streams. So your flash floods are common. It's responsible for most erosion in deserts. Wind primarily transports sediment, but these ephemeral streams are going to move a whole bunch when they actually happen. Let's see. Regions with internal drainage have ephemeral streams that do not flow out of the basin into the ocean. They just flow into a different part of the desert. So they're going to go downhill still, but not make it all the way to the ocean. So their example here are basin and range regions in the western U.S., which are characterized by over 200 small flat block mountains. And I've actually been around here. These are pretty nice. So a couple terms. Alluvial fans. Alluvial fans are going to be your deltas, but on dry land. So they're not going out into the ocean and spreading out. They're coming down off of mountains and other higher elevated areas, and they're going to spread out just at the bottom and not really move beyond that. Well, I think we'll see a picture in a second. Bajadas are created when several alluvial fans form adjacent canyons and merge, and then a playa lake forms when rainfall is sufficient to cover the entire basin floor. An example of that would be a salt flat that can form when water evaporates. When it rains, though, you get these really. So, is everybody familiar with like the Bonneville salt flats or any kind of salt flats? They go out there and race cars on them because they're really flat and really large. But if they get a lot of rain in the area, it becomes like a several inches thick, like huge lake that's just extremely shallow. And you can find videos of people going out there, and it just looks like they're walking on like a mirror because it reflects really well. So that would be like a playa lake. Continued erosion gradually diminishes the local relief. Eventually, only bedrock knobs called inselbergs remain. So here's an example. You have your block mountains here. So you have some erosion-resistant layers. You had some faulting, which tilted the layers up, and we'll kind of talk about this in another chapter. You had some faulting, which tilted the layers up, and so you get these rows of mountains. And so as it rains in this desert area, the water doesn't really get to go anywhere. It drains stuff off, but it doesn't make it to the ocean. It stays in these areas, and eventually, over probably millions and millions of years, the mountains get weathered away, and you just get flatter and flatter surfaces. The lakes become bigger and bigger and bigger as everything kind of flattens out. And they're suggesting that this large portion of California / Nevada, pretty much all of Nevada, and the southern area of Arizona and New Mexico have quite a bit of these types of land features. Here's an example. These are actual pictures of some. So here is an alluvial fan. You can see these mountain ranges, which are kind of like linearly stacked. And then as this feature comes out, you have this big alluvial fan. It all spreads out, just like a delta meeting the ocean. But there's no ocean, and it's probably not a like constantly running river. It just happens during the rainy seasons. And then us as humans are like, yeah, let's just build a road on top of it. Sure, every couple years we're gonna have to rebuild the road over and over and over again, but why not? This is a map probably of this. Yeah, you can see this is the exact same thing. So this is in Death Valley, and there's a little playa lake here. You can see the reflections from the water, and a couple alluvial fans they have highlighted here. And I can't read that. Does that say a shown? We'll see. So wind erosion, obviously we think of wind, moving things around in the desert. Moving air can pick up and transport your loose materials like sand. Similar to a river, the velocity of your wind increases with height above the surface, and the faster your wind's blowing, the more stuff it can pick up and erode away. Different from a river is it's less capable of transporting coarse material. When your river's flowing fast, it can pick up really big things. The wind's not ever really going to be able to do that. It's going to be mostly small material. Relatively insignificant erosional agent. It can really blow it around, but it's not really moving it into one specific area. Like water's always going downhill, always heading towards the ocean. Wind will blow it from one area to another, but that can change, and it can go back and forth with the wind, depending on the wind patterns. So we have some terms. Deflation is lifting and carrying of loose material, clay and silt only. And they call it deflation because as that stuff gets picked up and moved away, your landmass like literally drops down. Saltation, is rolling or skipping of larger particles along the surface. Blowouts are shallow depressions caused by deflation. So they're relating deflation to blowouts. And then desert pavement, they have an actual image of here. So we have the sand and a lot of large rocks mixed up. As all the sand blows away and you get your deflation, the large rocks kind of pile up at the surface because all the sand has been taken away from them. And so as you just drop this down and down and down, they don't have anywhere to go. So they just end up kind of piling up at the surface. Eventually, all the sand is blown away and you get this kind of desert pavement left over. As time continues, you get more sand blown in. But actually, one thing that happens about, like if you shake a bucket with large rocks and sand in it, the large rocks will come to the surface. You think they go to the bottom because gravity is going to be pulling on them more, but just the action physically of them moving like that is going to bring them to the top. So we only have a couple slides to finish up with tomorrow. We'll leave off there with wind deposits. Thanks for joining me today. Everybody have a nice day. See you tomorrow.